Hey folks, I'm Adam. This is the Machine Tech video blog, and today I'd like to talk about optical design for autocollimators. Now, I know that National Autocollimator Month is technically over, but hey, in my family we keep the festivities going well into June. In the last video, I discussed the mathematical formula which determines the sensitivity or resolution of an autocollimator. This formula is really at the heart of how an autocollimator works, but there are quite a few more details to consider if we're going to build a real working autocollimator, which is the end goal here. So in this video, I'm going to break down the design for the optical system in a simple autocollimator. I'm going to discuss each individual component from the light source to the eyepiece. This includes selection of appropriate components, their arrangement relative to one another, and quite a few relevant optics concepts which we haven't discussed yet. Heads up, this is going to be a pretty long video. In fact, in the previous video I had mentioned that I wanted to show some autocollimators with more complex designs in this video. But after seeing how much ground we needed to cover, I just decided to keep those examples for another time. So, without further ado, let's get this started. The first thing we need is a light source, and basically anything will do. Remember in the first video I used a flashlight because the autocollimator that I was using was missing the light source that it was supposed to come with. So really, not that big of a deal. The light doesn't have to have any special properties, it doesn't have to be of a specific color or anything like that. It just needs to be bright enough. Old school autocollimators used incandescent light bulbs like this one. If you're not familiar with how these work, inside of this glass is a vacuum. It's had all of the air pulled out of it. And then there's a small tungsten wire attached to two electrical leads. When an electrical current is passed through the wire, the resistance to that current causes the wire to heat up until it glows. This is kind of a brute force way of generating light, and incandescent light bulbs are not particularly bright, they are inherently inefficient, and they generate a lot of heat. A better option in every way is an LED, or light emitting diode. This might look a little bit like an incandescent light bulb, but it works completely differently by causing electrons to jump across a special semiconducting device called a diode, which is right there down inside of that little cup in the middle of the LED. These are much brighter, much more efficient, and they generate a lot less heat. So these have really become the technology of choice for a wide array of applications, including simple illumination, which is what we need in an autocollimator. The other nice thing is that you can get LEDs in any color you want. I prefer clear or white LEDs because this is just a more natural light, but there are some benefits to using light of a single color, which I'll talk about later. The next thing we need is a crosshair reticle. A crosshair reticle, sometimes called a graticule, is a piece of glass which has been engraved or etched with two intersecting perpendicular thin lines. It's called a crosshair because back in the day this would have literally been made out of two pieces of horse's hair, or sometimes out of individual strands of a spider's web. Now, plucking horses' manes doesn't sound that bad to me, but milking spiders sounds horrific, so I am really glad that they updated the technology. The crosshair is not the only pattern that you can get on a reticle. You can also get single lines or the classic bullseye. And truth be told, nowadays you can get an enormous variety of different reticle patterns, primarily for firearms, but also for things like microscopes and telescopes. Some reticles even have linear or angular graduations on them and can be used for measurement. This is something that we're going to take advantage of a little bit later. Another variation in reticles is bright field versus dark field. All of the reticles that I've shown you so far are bright field reticles. That means that there are opaque markings on transparent glass. So what you see is dark lines on a bright background, hence bright field. But you could have the opposite, thin slits in an otherwise opaque surface, and then what you would see is bright lines on a dark background, hence dark field. You will find autocollimators with dark field reticles. This can be very useful if you're trying to bounce light off of a low reflectance surface. It just shows up a little bit better, but it's not necessary. Since there are so many different kinds of reticle, and technically any of them will work here, we could more generically refer to this component as the target reticle. But since the crosshair is simple and traditional, it is still the most commonly used, and so I'll keep it as is. Okay, the crosshair reticle is placed at the focal length of an objective lens. Before I get knee-deep in lenses, let me reiterate what I just said. The crosshair reticle, not the light source, is placed at the focal length of the objective lens. If you placed the light source at the focal length, then what you would ultimately see in the autocollimator is the light source, not the crosshair reticle. But of course, it's the image of the crosshair reticle that we want to see. Whatever it is that you want the objective lens to project an image of is the thing that has to go at the focal length of the lens. Now, this may seem like a bit of a nuance, but the autocollimator is not going to work very well if you put the wrong thing at the focal length, so definitely keep this in mind. In this system, the light source is just providing illumination or backlighting for the reticle, and that's the reason why the exact type of light source doesn't matter all that much. Okay, let's talk about lenses. Do you remember this? This is the diagram that I used in the last video to illustrate the relationships in the autocollimator formula. The formula relates the tilt angle of the mirror to a displacement of the return image of the crosshair in the eyepiece. The key design parameter is this f sub L, the focal length of the objective lens. The greater the focal length, the greater the displacement for the same tilt angle on the mirror. It follows from this that ideally you would like to maximize the focal length of the lens, because that will essentially magnify the displacement and increase the sensitivity and resolution of the instrument. So between this 50mm focal length lens, and you can really see the curvature on that bad boy, and this 1000mm focal length lens, the choice seems fairly obvious. But the focal length of a lens is only one of two basic parameters of a lens. The other one is its diameter. And actually, this might be more appropriately called the aperture of the lens, because you can effectively reduce the diameter of a large lens by covering part of it up and only allowing light to go through a small hole. The aperture of the lens plays into the optical system of the autocollimator in a number of ways. The first one is perhaps fairly obvious. Because the lens is physically larger, it also gathers more light, which results in a brighter image of the crosshair and therefore makes it easier to read. The other way in which lens aperture plays in might be slightly less obvious. The idea is that you'll only be able to see a return image of the crosshair if the lens can collect all of the reflected light rays, right? So the mirror can't be too far away from the lens, and it also can't have too large of an angle. If the mirror is too far away, or if its tilt angle is too large, then only some, or perhaps none, of the reflected light rays will actually make it to the lens. In this case, you'll only observe a dim and perhaps clipped or partial image of the crosshair, or maybe no image at all. But we can potentially remedy this issue by using a larger diameter lens. If the aperture of the lens is large enough, then it might be able to collect all, or at least some, of those return rays. This has a direct effect on the working distance of the autocollimator, both in the maximum distance at which you can place the mirror and the maximum angular deviations that you can read at that distance. So for the reasons I just mentioned, larger apertures, meaning larger diameter lenses, are generally preferred. But the limiting factor here is cost. The price goes way up for larger diameter lenses. I mean, the price scales up pretty linearly for relatively small lenses, but as soon as you go above a certain size, all bets are off. Let's take these two lenses for instance. They're both 300mm focal length lenses, but this one is a 50mm diameter lens, and this one is 100mm. It's a whopping big lens, folks, and it cost a lot more than this one, certainly more than twice as much. And of course, this is going to be super ultra mega true if you need special and precision lenses, which we do, by the way, but I'm getting ahead of myself. For reasons which I'll discuss in just a moment, larger diameter lenses also produce images with greater distortion. But yeah, in general, if you can afford it, the bigger the better. Here's the issue, folks. So far, we've only been talking about ideal scenarios in which all of the light collected by the lens is focused down to a single focal point. Actually, it would be many, many, many focal points along a focal plane, depending on which angle the light was coming into the lens from. And actually, that's why we see images formed by lenses rather than just single points of light. But that's not the point here. Not all of the light focuses down to a single point. And this is due to properties of light, properties of the materials used to make the optical components, or due to defects in the optical components themselves. Any of these factors which lead to light not coming to a single point of focus is called an aberration. And correcting for aberration is a lot of what optical design is all about. In an autocollimator, there are two big aberrations that we have to deal with: chromatic aberration and spherical aberration. So first, chromatic aberration. Remember that lenses are able to manipulate light because light bends when it travels from one medium to another if those media have different densities. This is called refraction. How strongly a material refracts light is given by a unitless number called the index of refraction, or refractive index. But there's something else going on here. It turns out that how strongly light is refracted or bent depends on its color. And light on one side of the spectrum, like violet and blue, is refracted more strongly than light on the other side of the spectrum, like orange and red. This phenomenon is called dispersion. That means that blue light, which is refracted by a lens, comes to a focus closer to the lens than, say, red light. And then green light, which is in the middle of the spectrum, is kind of in between red and blue. You can't see that in this setup because these light sources are lasers, and lasers are monochromatic. But if this light source were generating true white light, which contained all of the colors in the visible spectrum, then this is what you would see. Where light passing through the center of the lens isn't refracted at all, or at least not very much, and so all of that light just kind of travels along a straight line. But the light which passes through the periphery of the lens is refracted considerably, and therefore all the different colors in that white light will focus at different points. I mean, different points axially along this optical axis. This is bad because you can't focus on all of the colors at once. So that means that the image that you view in any imaging system that uses refractive optics, including our autocollimator, is going to be blurry. And that's chromatic aberration. Fortunately, there's a way to correct for this, and it involves combining two lenses made out of different glasses with different amounts of dispersion. So you've got a convex converging lens made out of a low dispersion glass called crown glass, and you've got a concave diverging lens made out of a high dispersion glass called flint glass. And you smush them together with a little bit of glue, and the dispersions of the two lenses cancel each other out, and boom, chromatic aberration corrected. Now, it's not perfect. With just two lens elements, you can't correct for all of the colors. You can only correct for two, usually red and blue. This is a design parameter. But this is already a huge, huge improvement. This style of lens is called an achromatic doublet. Achromatic or achromatic, meaning without color, but here really meaning without chromatic aberration, and doublet because it's actually two lenses glued together. Here's an example of a nice little achromatic doublet. And from the side profile, this actually kind of just looks like a plano convex lens, where one side is flat and all of the required curvature is on the other side. But if you look really closely, you can actually see where the two lens elements meet. And this one has been glued together with optical cement, but they actually don't have to be. And like this one right here, essentially the same lens, but you can see that this one is in two pieces. So this is the convex crown glass element, and then this is the concave flint glass element. And they're just designed to nestle into one another just like that. Of course, just like any other lens, they come in many, many different sizes. Like here's a really small one, which I think is just adorable. But they also get much, much bigger. As you can imagine, achromatic doublets are much, much more expensive than simple single element lenses. Like if you wanted to buy an achromatic doublet in this size, 50 millimeters, you're looking at something like $150. And if you wanted to buy something in this size, 100 millimeters, you're looking at more like $1,000. Although this would definitely be overkill, you can see that the prices are significantly higher, but they are definitely worth it. Now, I know you folks out there in YouTube land are pretty smart, so you're probably thinking to yourself right now, well, why do you even need to use white light in an autocollimator? Why don't you just skip this whole chromatic aberration issue and use a monochromatic light source? Like a colored LED, or a laser diode, the type that you would find in pen lasers. Then you could skip the expensive achromatic doublet and get away with just a simple single element lens. And that's true, but even if you use monochromatic light, there are still benefits to using an achromatic doublet as the objective lens in the autocollimator, because achromatic doublet lenses also correct for the other main type of aberration that we have to deal with, spherical aberration. So far, I've been talking about simple lenses with spherical surfaces. That means that the curvatures on the two sides of the lens can be fully defined by a single parameter, their radii. The problem is that spheres don't focus converging light rays to a single point. In fact, light rays at the center of the lens focus at a distance further away from the lens than do light rays at the periphery of the lens, which focus at a shorter distance. Again, this means that we can't focus on all of the light rays simultaneously, and this results in a blurry image due to what we call spherical aberration. This setup isn't demonstrating this aberration because we're only tracing 3 light rays, one in the center of the lens, which doesn't refract anyway, and 2 other peripheral rays, which are equidistant from the center, and so we do expect them to converge at the same point. But if we were to trace more rays, this is what we would see, where light rays closer to the center of the lens focus at a longer distance from the lens, and light rays closer to the periphery of the lens focus at a shorter distance from the lens. By the way, spherical aberration is more noticeable with greater curvatures, meaning shorter focal length lenses, as well as with larger apertures, meaning larger diameter lenses. Now, there are ways to deal with spherical aberration, and perhaps the most obvious way is to just not use spherical surfaces on the lenses. There are other geometric shapes which are capable of focusing incoming light rays to a single point, and lenses which are defined by those geometric shapes are called, not surprisingly, aspherical lenses. So why don't we make all lenses with aspherical surfaces? You guessed it, cost. Spherical surfaces are way easier to make than aspherical surfaces. I mean, they basically make themselves. If you take 2 surfaces and put a little bit of abrasive between them and then rub them together, they sort of naturally generate spherical surfaces. And you know, within a certain range of aperture, a spherical surface is very close to being perfect, but it's not quite perfect, so we'd like to be able to correct for spherical aberration if we can. Another way to correct for spherical aberration without having to generate trick aspherical surfaces is to use multiple spherical lens elements. By playing around with the radii of curvature of the 4 faces on the 2 lens elements in an achromatic doublet, optical engineers can effectively correct for spherical aberration. But just as with chromatic aberration, this correction is not perfect. With 2 lens elements, you can only correct spherical aberration for a single color, usually green because it's right in the middle of the visible light spectrum, but this is also a design parameter. Anyway, this is the reason why it's still worth it to use an achromatic doublet in an autocollimator, even if you use a monochromatic light source or filter white light in some other way. Okay, we've got our objective lens, an achromatic doublet with a very long focal length and a nice wide aperture. And the next thing we need is a mirror. And this doesn't really need to be a mirror per se. Any flat reflective surface will do. You can even use something like a gauge block. That's actually fairly common. So perhaps this component would be more appropriately called a plano reflector. But mirrors, and by the way, what I mean when I say mirrors is a material which has been coated with another reflective material. The typical combination is metal on glass. Mirrors are definitely the device of choice for this application. But I'm not just talking about any mirror, okay? I'm talking about first surface or front surface mirrors. Here's an example of the type of mirror that most of us are familiar with, the type that's in your bathroom. It's a glass plate that's been coated on one side with a reflective material, a metal, usually aluminum. Now, this coating is actually pretty fragile and it can be easily scratched off. So, in order to increase the durability of the mirror, the coating is applied to the back side of the glass. You look through the glass at the reflective coating. This is what's called a second surface mirror. The second surface is the back side of the glass, and the first surface is the front of the glass. Now, this works just fine for inspecting your hair in the morning, but it's not appropriate for optical systems. There are a number of problems here. Let's say that an incident light ray hits a second surface mirror. It encounters the glass surface first. Now, glass is mostly transparent, but it does have some reflectivity. So about 8% of the light bounces off of the first surface, and only about 92% makes it to the second surface. The second surface has been coated with aluminum. It's mostly reflective, but it's not perfect either. So only somewhere between 90 to 99%, let's say 95% of the light that makes it to the second surface is reflected. The rest of it is scattered. So 0.92 times 0.95 equals 0.88. This means that only 88% of the incident light emerges as reflected light from the coated second surface, and this loss of light results in a dimmer image. But it's actually worse than that, because the small amount of light reflected from the glass first surface will show up in the imaging system as a faint secondary image, what's called a ghost image. And since the light that reflects off of the coated second surface has to travel through the glass twice, refraction and any optical defects in the glass will cause aberrations in the final image. Yikes. The solution is to apply the coating to the front of the glass. This is what's called a first surface or front surface mirror. Now you get a brighter image and you don't have to deal with distortion or ghosting. But you do have to be very, very careful when handling the mirror because the reflective coating is unprotected and ridiculously delicate. The way they typically make first surface mirrors is that they take a relatively thick hunk of good quality glass and then grind it, lap it, and polish it so that it's extremely flat. Then they put it in a vacuum chamber along with a piece of aluminum and some heaters. When the aluminum is heated, some of the particles are deposited onto the glass in a very thin, very uniform layer which retains the overall shape. And then you've got yourself a first surface mirror. An even thinner protective coating of silicon oxide is also usually applied on top of the aluminum. Back in the day, the coating would have been silver, applied through a chemical process. But since silver tarnishes, the development of the aluminum vacuum deposition process did away with silvered mirrors. Although I have to say that silvering is still much easier to do if you want to attempt making your own DIY first surface mirror. Although aluminum is the most common, other metals are used too. For example, gold in this laser mirror. Or rhodium, as in this dental mirror. Evidently, rhodium is actually durable enough to be jammed into someone's mouth, but it will wear off eventually with use. This is what a mirror looks like when the coating has been damaged. Now, for reasons I don't want to get into here, these scratches or any other kind of break in the reflective surface won't show up in the reflected image of the crosshair in an autocollimator. Essentially, it just reduces the surface area of the mirror, resulting in a dimmer image. Now that's important to know, because precision first surface mirrors are not only delicate, they're also expensive. A winning combination, if ever I heard one. So if you find a really good deal on a slightly damaged mirror, it may still be perfectly usable. Here's one way to tell the difference between a second surface mirror and a first surface mirror. Place an object, like a pen, directly on the first surface of the mirror. If there's a gap, as there is here, between the pen and its reflection, then it's a second surface mirror. And this is actually kind of cool because you can even see the faint ghost image. If there's no gap, then it's a first surface mirror. But I wouldn't recommend poking an expensive mirror like this. I've mentioned the word precision at least a couple times now, and this is a good point to stop and discuss what that word means with regard to optical components, because nowhere is precision more important in an autocollimator system than in the target mirror. Let me show you why. Just a quick recap here. Imagine that the laser beams coming from this light source are the collimated light rays coming out of the autocollimator. If I place a mirror in the path of the light rays, then they will be reflected back toward the autocollimator at an angle equal to twice the angle of the mirror. That's the law of reflectance. I've already talked about that. But notice that the rays remain parallel to each other. All I've done is change their direction. That is to say that the light is still collimated. And because it's still collimated, if the angle of the reflected light is shallow enough to make it back to the objective lens in the autocollimator, then it will be refocused to a single point somewhere on the focal plane of the lens. This is the ideal scenario. This is how an autocollimator is supposed to work. But what if the mirror isn't perfectly flat? Here's a model of a mirror which is not flat. It has a concave reflective surface on one side and a convex reflective surface on the other side. And actually, this is a pretty good example because the way that optics are manufactured, errors in the form of the surface usually come as uniform curvatures like this, rather than as localized inconsistencies or random shapes. But watch what happens when I put the convex surface in the path of the light rays. Okay, there we go. Let's look at that. So we've got parallel incident rays, but diverging reflected rays. This means that the reflected light is no longer collimated. Let me flip the mirror over to the concave side. Okay, now we've got converging reflected rays. The light rays converge at the focal point of the mirror, but then they begin to diverge again on the other side of the focal point, and we're back to where we started, so this isn't any better. In both of these cases, even if some of the light makes it back to the objective lens, it will not be refocused at the focal plane. That means that you won't be able to see the return image of the crosshair. At best, what you'll see is a fuzzy blob, and probably not even that. This is an important point, so let me reiterate. If the target mirror is not flat, it's not that there will be an error in the position of the return image of the crosshair in the eyepiece of the autocollimator. The return image of the crosshair simply won't form at all. And this is a really exaggerated example, but even very, very small curvatures will spoil the image. The mirror really needs to be dead flat. But of course, there's no such thing as perfection in nature, so some amount of error in the form of the mirror has to be tolerated. So how flat does the mirror really need to be? Well, we're talking about extremely tiny values here, deviations from perfect form of just a few micro-inches. That's millionths of an inch, or around 100 nanometers. And that brings up an interesting question. How do you even measure something that small? As a self-professed metrology nerd, that turns out to be one of the most fascinating aspects of optics, because in order to measure errors that small, you have to use light itself as the measuring tool. When you place two very flat reflective surfaces in contact with each other, like let's say the top of this polished steel disc and the bottom of this polished glass disc, and then shine monochromatic light on them, like let's say from this helium gas discharge lamp, then something magical happens. A distinct pattern of alternating bright and dark light bands called fringes appears. Now, what the heck is going on here? Basically, it's due to the wave nature of light and a phenomenon known as wave interference. This video is really not the place for a full discussion of this amazing phenomenon, but it's very important for defining precision in optical components because it can be used to measure flatness and spherical curvatures with a technique called interferometry. Here's a nutshell version. The fringe pattern depends on the gap between the two surfaces. Therefore, it tells us something about how closely the two surfaces match each other in terms of their shape. For flat surfaces, the straighter the fringes, the more closely the surfaces are matched. And the more the fringes are curved, the less closely the surfaces are matched. If one of the surfaces, let's say the bottom of the glass disc, is known to be very, very flat, then we can use it as a reference to evaluate the flatness of the other surface, in this case the top of the steel disc. So if the fringes are really straight, we can say more than just that the two surfaces match each other. We can also say that the test surface is very flat. But it's actually better than that. We can quantify exactly how flat the test surface is using the ratio between the curvature of the fringes and the spacing between the fringes, as well as the color of the light used. Now, when I say color, I mean wavelength. I'm not going to get into it except to say that wavelength is a property of light closely associated with color. It's a physical dimension, which for visible light is measured in tens of microinches or hundreds of nanometers. Let's bring it back in and take a look at this first surface mirror. There are three common grades of flatness for precision optical components: quarter wave, 1/10 wave, and 1/20th wave. The flatness spec for this mirror is listed as 1/10 wave. That means that when this mirror was measured using the interferometry technique I just described, the total error in flatness, the total variation in height from the highest point on the surface to the lowest point on the surface, was less than or equal to 1/10 of the wavelength of light used to produce the fringe pattern. The standard wavelength for these types of measurements is 632.8 nanometers, or 24.9 microinches, which is the wavelength of the red light produced by a helium neon laser. So this mirror is flat within about 63 nanometers. That's 2.5 microinches, 2.5 millionths of an inch. 0.0000025 inches. That's ridiculously flat, folks, but that's about what we need. Quarter wave is really the absolute minimum acceptable flatness spec. 1/10 wave is ideal, and 1/20th wave is a little overkill, and the cost wouldn't really be justified. By the way, the process for evaluating the so-called irregularity of the spherical curvature of lenses is very similar to the process for evaluating the flatness error of mirrors. And the irregularity of the precision objective lens in an autocollimator should be quarter wave or better. I hope that all made sense. It's an important thing to understand when you're sourcing optical components. Okay, so we've got our target mirror, a precision first surface mirror. The mirror is reflecting the collimated light back into the objective lens, and now we need a way to view the return image of the crosshair because the light is going to refocus somewhere over here. So in theory, we could put our eye somewhere in this area back at the beginning of the optical path. In fact, that's what was implied by the simplified diagram I used to illustrate the relationships in the autocollimator formula. However, in practice, this isn't really feasible because there are just too many obstructions: the light source, the crosshair reticle. And by the way, we don't need to see the original crosshair. The relationship of the return image of the crosshair to the original crosshair on the reticle is irrelevant. We only care about tracking the change in the position of the return image. Anyway, what we really need is a way to redirect the return image of the crosshair to a place where we can more easily view it. We need a beam splitter. A beam splitter is an optical device which allows some portion of an incident light beam to pass through it and reflects the other portion. In our autocollimator system, this will allow the projected image of the crosshair to pass through to the objective lens, but it will redirect the return image at some angle which depends on the orientation of the beam splitter. The beam splitter surface is usually oriented at 45 degrees so that the reflected light is redirected at twice that, 90 degrees, or perpendicular to the optical axis. So what is a beam splitter? In essence, it's just a partially reflective mirror, and in its simplest form, it really is just a glass plate where one surface is coated with a thin layer of reflective material to allow partial transmission and partial reflection. This type of beam splitter is called a plate beam splitter. Plate beam splitters are inexpensive and easy to manufacture, but since they're basically just second surface mirrors, they suffer from all of the same problems as second surface mirrors: loss of light, ghosting, distortion. So a better design for precision optical systems is a cube beam splitter. A cube beam splitter is made by taking two triangular prisms and then gluing them together on their hypotenuses. Here you can see the split line between the two halves, and it's the hypotenuse which is the reflective surface. I should mention that the ratio between transmission and reflection is a parameter that you can select when you order a beam splitter. In an autocollimator system, a 50-50 split is appropriate, 50% transmission and 50% reflection. Now, just like the other components I've mentioned, the reflective surface of the beam splitter should be very, very flat, quarter wave or better. But otherwise, this style of beam splitter doesn't suffer from the same types of disadvantages as plate beam splitters do. So beam splitters come in these two basic shapes, but I should also mention that they come in a few different types. Some beam splitters, called dichroic beam splitters, have special coatings that allow them to split the light according to its color. So they transmit some colors, but reflect others. Now, that's a pretty cool effect, but we don't need that. And some of them, called polarizing beam splitters, either have special coatings which allow them to split the light according to its polarization, or they're made out of special transparent crystals, like quartz or calcite, which exhibit a very interesting property known as birefringence, which means that they have two optical axes. Now, this is another very, very cool effect, but it's not needed here either. Okay, so we've got our precision, non-polarizing cube beam splitter that's redirecting the return image of the crosshair at 90 degrees so that we can view it more easily. As the tilt angle of the mirror changes over here, we'll be able to see the position of the return image changing over here. Now we need some way to quantify that change in position, that displacement. We need a scale reticle. Now, I already mentioned scale reticles when I talked about different kinds of reticles, and this is the same type of glass disc with some kind of a pattern marked on it, but the pattern in this case should have either one line or two crossed lines with linear graduations at regular intervals. Now, before I discuss scale resolution, let me just point something out. In order to compare the position of the crosshair to the graduations on the scale, we need the return image of the crosshair to be superimposed on top of the scale on the reticle. The return image has to come to a focus on the same plane as the scale, which means that both the crosshair reticle and the scale reticle have to be at the focal length of the objective lens, a very important point to keep in mind. Following the autocollimator formula, we've maximized the focal length of the objective lens to get the largest displacement for the smallest change in mirror angle. Now, in order to get the highest resolution, the next thing that we'd like to do is subdivide the total range of displacement into the smallest possible increments. That means using a scale reticle with very small graduations. Scale reticles are typically graduated in 1 mm, 0.1 mm, or 0.01 mm increments, although reticles with other scales can also be custom ordered. Here's an example of a reticle with a 0.1 mm scale. That's about 4/1000ths of an inch per division. I mean, that's really small. You can barely even see that. Let me go ahead and zoom in. There we go. That's the best that I can do on the camera. I mean, that is really small. But that's actually not even as small as it gets. Here's one with a 0.01 millimeter scale. That's about 0.4 of an inch per division, which is ridiculously tiny. You can't even see the graduations with the unaided eye. Here's what it looks like blown up in a microscope. Folks, this is really right at the practical limit of what can be made with conventional manufacturing techniques and what can be seen with conventional optics. We do get a little boost in resolution because the human eye can accurately interpolate to approximately 1/4 of a graduation, but it takes practice. It's definitely not an easy thing to do. And as I've already demonstrated, it's impossible to do without some way to magnify both the scale on the reticle and the return image of the crosshair. So the final component that we need in a real working autocollimator is an eyepiece. An eyepiece, sometimes called an ocular lens, is a magnifier. And the most basic eyepiece is constructed from a simple biconvex lens, just like the one used in a magnifying glass. In order to get the highest resolution in the autocollimator system, we need an eyepiece with a relatively high magnification so that we can use a scale reticle with smaller graduations and track smaller displacements of the return image of the crosshair. But, slightly confusingly, the rule of thumb for using focal length to select a lens for an eyepiece is essentially the opposite as for the objective lens. For the objective lens, the longer the focal length, the higher the magnification. For the eyepiece, the shorter the focal length, the higher the magnification. So I'm going to use this logo, which I'm going to call the object, and this 50 millimeter focal length biconvex lens to demonstrate this concept. If I drop the lens between the object and the camera, then what we see is an inverted image. And whether it's magnified and by how much it's magnified depends on the focal length of the lens. The longer the focal length of the lens, the more the object will be magnified. But this set of rules or behaviors only applies when the object is at a relatively long distance from the lens relative to its focal length. So when I start to move this closer to the object, there's a point at which everything goes kind of funky. And then the image appears right side up again. Let me move a little bit closer. So now we can see that when the object is at a relatively short distance from the lens relative to its focal length, then what we see is a right side up image, not inverted. And it is magnified, and the amount of magnification is still dependent on the focal length of the lens, but now the rules are kind of switched around. Now, the shorter the focal length of the lens, the more the object will be magnified. This is essentially because you can move the lens closer to the object, which will make it appear larger. I don't really want to get into this, but some simple ray tracing diagrams could prove this out. I'd also like to point something else out, which is that there's quite a lot of glare or unwanted reflections off of this lens. And that's a thing that happens in an optical system as well. So you can get lenses that have anti-reflective coatings on them that cut down on stray light and unwanted reflections. And it's always a good idea if you can afford it. One big problem with simple magnifiers is that optical aberrations like the ones I mentioned earlier in this video are more pronounced at short focal lengths. Using an achromatic doublet instead of a simple single element lens will certainly help, but real eyepieces usually have 3 or more, sometimes many more lenses, to form a more or less self-contained optical system corrected for aberrations. If you pick up a book on amateur telescope making, you'll find lots and lots of different eyepiece designs. Many of these you could make yourself without too much trouble. One eyepiece design in particular, the Plissel eyepiece, which is constructed from two achromatic doublets with the crown glass elements facing each other, is, I think, an especially good candidate for a shop-made eyepiece because it's simple and easy to make and also produces a very nice, well-corrected image. But you can also buy any of these eyepieces that you want ready-made for not too much money. I have to say that most, but not all, eyepiece designs will work in our autocollimator system. A few of them, especially some of the really old designs and some of the really new designs, have focal planes inside of the eyepiece, between the lens elements, so you can't really get a reticle in there. But as long as the eyepiece has an external focal plane and can be focused on a reticle, then it should work just fine. Commercially available eyepieces are intended primarily for telescopes and microscopes. And the system for specifying magnification is different for each. Don't you just love it when they make it easy like that? For telescopes, the focal length of the eyepiece is specified, and the range of available focal lengths is somewhere between 2 millimeters and 40 millimeters. Here are a few inexpensive ones I had lying around. 25 millimeters, 17.5 millimeters, 9 millimeters, and 4 millimeters. Remember that the shorter the focal length, the higher the magnification. So the 4 millimeter eyepiece will magnify the return image of the crosshair and the scale on the reticle the most, and the 25 millimeter eyepiece the least. For microscope eyepieces, the magnification of the eyepiece is specified. The most common magnification by far is 10x, but you can also find 15x and 20x eyepieces, although I don't have a 20x eyepiece here. Now, thankfully, there is a simple formula for converting from magnification to focal length and vice versa. Magnification equals 250 divided by focal length in millimeters. The 250 is something I won't get into, but it's a constant value used in this formula. So if you do the math real fast, you'll see that, for example, a 10x microscope objective is roughly equivalent to a 25 millimeter telescope objective. Take your pick, as long as it can focus on a reticle. And some eyepieces, by the way, already have the reticle inside of them. Ho, 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 ho. But I'm getting ahead of myself. There you have it, folks. At long last, we finally have a complete optical design for a real-life, honest-to-goodness autocollimator of a basic type. I wasn't sure we were ever going to get here. I mean, how many minutes are we into this thing? But I hope that it wasn't too painful. We actually have everything that we need now in order to make one of these suckers. And that's what I'm going to do in the next video. I'm going to design and build an autocollimator prototype. In fact, this is it right here. I'm really excited about it. But in any case, this video is way too long already. So that's it from the Machine Tech video blog. As always, I hope you learned something.